Bismillahirrahmanirrahim. Assalamu alaikum. I'm Fakhr Lodi and this is our 44th lecture of Formal Methods for Software Engineering, and we are discussing Petri nets. In the last two lectures we discussed Petri nets and we saw how can we use Petri nets to specify the behavior of some of the concurrent systems or some very famous problems that we see in concurrent systems. So we saw how easily can we use these systems to do that. So that is the real power of Petri net. Once again, remember that Petri nets can be used for many different purposes, including modeling finite state machines. But the best use of Petri nets is in the domain of concurrent systems. Concurrent systems can be specified with some other tools such as CSP and so on and so forth. But this Petri net is a very powerful mechanism because the representation here is graphic, and because of the graphic nature of the representation, it is easier to see what is happening, and it also gives you a good understanding of what the dynamic behavior of the system is going to be. And this is where the concurrent systems, they are very, very difficult to understand. Talking about the dynamic behavior of the concurrent system. Anyway, last time we were discussing the behavioral properties of concurrent systems, and we mentioned some of the properties. We will now resume our discussion from that point, and we will start with a few properties that we need to understand and observe in a Petri net and see what is the significance of those properties. The first property that we discuss in the context of Petri nets is what is called reachability. Reachability is a property which tells us whether we can reach a state from a given state. That is there any possible sequence of transitions with a given marking in the Petri net that will take us from a given state to another specific state. If we can find such a sequence, that means this state is reachable from the state from where we started with the given marking. Please remember that in a Petri net, we have the static nature of the Petri net, which is just a directed graph, and we also have the dynamic component of the Petri net, which is given by the information in its places with the help of the markings or the tokens that we have. So tokens, they give us the dynamic behavior of the Petri net. So we try to find a mapping, a sequence of transitions that will take us from one state to the other, and then we say that this Petri net, this state is reachable from that state. This reachability has a very significant impact on the overall characteristics of this Petri net. When we will talk about the deadlocks, starvations, and those kind of things, then we will discuss that in more detail. But basically what we are saying here is that if a given state is reachable from another state, and if we can kind of make a complete matrix and say which state is reachable from which state, with the given marking, with the initial marking that we have, that means we can say that the system is live in many cases. So the liveness of the system is another property that we talk about, and that property tells us whether the system or the Petri net for which this system is designed, is it live or it will eventually be dead. A live system will be a system in which we will continue working, and a dead system will be where eventually you reach a state from where you cannot move any further. So liveness is yet another very important property of a Petri net, and we want our Petri nets to be live so that we can continue the process. The third property that we will talk about is the concept of boundedness. Boundedness means that do we have in a particular Petri net this property that any given place will never have more than a fixed number of tokens in it, no matter what the sequence of transitions may be, no matter in which sequence these transitions are fired, we will never get more than a specific number of tokens in a particular place. If that happens, then we say that this particular Petri net is a bounded Petri net. So these three basic properties, reachability, liveness, and boundedness, these are important properties. We have already talked about the relationship between reachability and liveness. The boundedness also has a very important impact on the overall characteristic or behavior of the Petri net. It means that there will never be an overflow. A place represents maybe a repository where you can put your information, for example, a buffer or something like that. Here we are saying that it will never be the case that this buffer or whatever is being modeled by this particular place, this is never going to overflow, and this is going to handle the volume of transitions that we are going to expect in our Petri net. And if that does not happen, that means that eventually this place will be, there will be overflow, because if it cannot be bounded, that means we can eventually have infinite number of tokens, and we can never handle infinity in any system. So boundedness is yet another very important property of a Petri net. So let us look at what is meant by reachability with the help of an example. So let me take you onto the slide. Here is a Petri net in which we have two places, and these places are red and black, and we have a set of states, and these states are BR, RR, and BB. If we try to analyze this thing, with the initial given marking, that is, we have 3 tokens in our red place and we have 2 tokens in our black place. So when the first transition is fired, that is from red, this transition BR is fired, so that it takes a token from both the red place and the black place and deposits 1 token back into the red place. So if we started with this 3-2, we will have 3-1 after this transition is fired. If we look at the other transition, that is RR, in this particular case, it takes 2 tokens from the red place and deposits 1 token into the black place, and hence this transition results in the state, that is, it will have 1 token in the red state and 3 tokens in the black state. If we fired this state BB from the initial marking, this BB transition takes 2 tokens from the black state and deposits 1 token back into the black state. That means after we have this transition BB, we will have 3 tokens in the red place and 1 token in the black place. So if we started with this state 3-2 and we fired the transition BB or BR, we will end up in a state 3-1 that represents 3 tokens in red place and 1 token in black place. And if we fired token RR from there, that means we will end up in the state 1-3. When we are in state 1-3, we can either fire BB or BR. We cannot fire RR because that requires 2 tokens in red state. So these are the only 2 transitions that can be fired. That will result in 1-2. That is 1 token in red state and 2 tokens in black state. If we were in this state 3-1, from 3-1 we could fire RR or we could fire BR, but we could not fire BB because that required 2 tokens in the black place. So when we fired RR, we will end up in a state 1-2, and if we fired BR, we will end up in a state 3-0. From 1-2, we can fire BB or BR. That will take us to state 1-1, and from 3-0, we could fire RR. That will again take us to state 1-1. From 1-1, there is only one transition that is enabled, that is BR, because it requires 1 token each from red and black, and it will take these tokens and it will deposit 1 token into red, and we will get into the state 1-0. Now, after we reach the state 1-0, at this point in time, no transition will be enabled. That means we cannot move any further from this point. So what happens here? We started with an initial marking. From that initial marking that defined the state of the Petri net, and we say that from that initial point in this particular case, there are 7 reachable states. You can reach 7 different states. And there is one state which is a dead state among these 7. That means you cannot move any further. So reachability is one thing. What you do is you kind of make a graph like that of different possible transitions that you can fire, and then see which state is reachable from which particular state. Reachability is a decidable problem. You can tell about the reachability that can be calculated, but it is an exponential problem. It is not a linear time, it's an NP time problem. So you can decide about reachability, but it is non-trivial. It is NP time complexity problem. The other issue, related issue, is the issue of liveness. Whether a transition is live or not. It is quite possible that we reach a point where we cannot do anything. When such a point is reached, we say that we are in a deadlocked situation. No transition can be fired. But it is still possible to fire certain transitions, whereas some transitions are disabled. That is also some very important analysis that we have to do to see which transitions they remain enabled and which transitions have a possibility of going into a kind of a dead situation where they will eventually never be fired. And if we ultimately reach a situation where nothing can be done, that means we are at a deadlock situation and we cannot move any further. Remember that in concurrent systems, deadlock detection and then coming out of the deadlock is a very important thing. So we first have to understand in a concurrent system whether a deadlocked situation can arise or not, and if we see a possibility of a deadlock, in that particular case, we have to remodel our system so that we cannot have a deadlock. So let me show you an example where we have a non-live Petri net. So we have some transitions and some places. So we have a similar pattern here. So this is our static Petri net. The initial marking is, let us give the names to the transitions. This is T1, this is T2, this is T3, and this is T4. And we have this place, let's call it P1, this is P2, this is P3, and P4. So the marking says that we have 1, 0, 0, 1. One token in place 1, no token in place 2 and 3, and 1 token in place 4. Now when we have this system, only one transition is enabled, and that is T1. So when that transition fired, we get a token in this place. So from here, we reach a state which is 0, 1, 0, 1. At this point in time, we have two transitions that are enabled, that is T2 and T3. If we fire T2, this token will be taken from here and it will be deposited here, so we will come back to our original state. So if T2 is fired, we come back to the original state, so we will keep on doing that. If T3 is fired, in that particular case, we will take these two tokens from here and deposit it here. So we will have, from here, we will have the state 0, 0, 1, and 0. At this point in time, we have only one transition that is enabled, which is T4, and that will take this token from here and deposit the token in P4. So we will get 0, 0, 0, and 1. This is the state. And at this point in time, no transition is enabled because this transition requires token here as well, and we do not have a token in place 2. That means we cannot fire any transition from this point onward. So this is a deadlocked state. So when we reach this state, system is no longer live, it is a dead system. So you saw here what can happen to a Petri net. And this kind of analysis is very important because we don't want to get into a situation where eventually we cannot do anything in the system. Okay, so we need to do this kind of analysis and try to identify whether we can get into a non-live situation in a Petri net or not. Let me show you an example of boundedness where the system is live but it is unbounded. जैसा कि आप देख रहे हैं, we have a Petri net, very ordinary looking Petri net, but this is an example of an unbounded but live Petri net. Let us give it an initial marking and let us put a token in this place P1. Now this place P1 gets one token. So this is our initial state. So the transition T1 is now enabled, and this marking is written as this vector 1 0 0 0 0. So this vector 1 0 0 0 0 denotes this Petri net with initial marking with one token present in place P1, and the transition T1 is enabled. Now we fire this transition T1. Let us see what happens. When T1 fires, it will take one token from P1, and it has two outputs, that is P2 and P3. So it will deposit one token each into P2 and P3. So let us do that. So now we have done that, and as you can see, we have a token in place P2 and P3, and the transitions T2 and T3, they are now enabled. Now we can write this vector M1 is equal to 0 1 1 0 0, which denotes this particular position or this situation in this Petri net. Now you may have observed one thing here. We started with only one token in P1, but if we look at the Petri net, it has two tokens now. So we have one more token now present in the Petri net than the number of tokens that we started with. Let us now look at it in more detail, and let us fire some more transitions and then see what happens. Now both these transitions T2 and T3, they are enabled. So we fire T2. When we fire T2, the token is taken from P2 and is deposited in P4. Note one thing here, that we will fire only one transition at a time because that is what the requirement in a Petri net is. You cannot fire both the transitions. So now this situation that we have is, we have this vector M2 which is 0 0 1 1 0, which basically tells us what the situation of the Petri net is, what the marking of this Petri net is. Note one thing here, that after firing T2, since T4 needs one more token, one token in P5 and there is none there, hence T4 is not yet enabled. So the only transition that is enabled that we can fire is this T3. When we fire T3, token from P3 will be taken and it will be deposited in P5. So that is what happens. So now this situation is now this vector M3, which is 0 0 0 1 1. Now we have tokens in places P4 and P5, and hence the transition T4 is enabled. Now this transition T4 will be fired because this is the only transition that is enabled, and it will deposit one token in P2 and one token in P1. It will take both these tokens from P4 and P5 and deposit these tokens in P1 and P2 respectively. So that is what happens, and we do that. Now we have a token in P1 and P2, and the transitions, that is T1 and T2, they are enabled. Now, if we look at the vector, we have 1, 1, 0, 0, 0. Note one thing here, from this marking M1 to marking M4, we have these vectors, that is M1 was 0, 1, 1, 0, 0, M2 was 0, 0, 1, 1, 0, M3 was 0, 0, 0, 1, 1, M4 is now 1, 1, 0, 0, 0. So in all those transitions, the markings that we got from M1 to M4, the total number of tokens did not change. In the initial case, we started with only one token, that is M0, but subsequent transitions, they did not add anything, add any token to our system. So the total number of tokens, they remained the same throughout these 4 transitions. But now, once again, T1 is enabled. Now, T1 is enabled, as we can also see that T2 is also enabled. So, but let us fire T1 and then see what happens. So when we fire T1, it will take this one token from P1 and a token will be deposited in P2 as well as P3. So let us do that. Now we have 2 tokens in P2 and 1 token in P3, and the transitions T2 and T3, they are enabled. And the marking M5 now is 0, 2, 1, 0, 0. Note one thing here, what has happened here is that when we fired T1, it took 1 token from P1 and it deposited 2 tokens, one in P2 and another one in P3. Hence, the total number of tokens that we now have in our system, they are 3. So, once again, 1 token has been incremented. We started with only 2 tokens, marking M4, and in the marking M5, we have now 3 tokens in the system. The same thing happened in M0 and M1. In M0, we had only 1 token, and in M1, we have 2 tokens. So similarly, in M4, we had only 2 tokens, and in M5, we now have 3 tokens. So 1 token has been added. Now you can see the phenomena, what is happening here. So what we can see here is, whenever transition T1 fires, it takes 1 token from the enabling place and it deposits 2 tokens in the outputs. So 1 token is incremented. Every time T1 will be fired, we will have 1 more token in the system. And this can result in an infinite number of tokens, and hence we have a problem. Now this PetriNet is a live PetriNet, but it is unbounded and it will not be controlled after some time, because the number of tokens they present, the buffers, the storage space, whatever we have, it cannot be unbounded. So this kind of PetriNet is not a good PetriNet. So we need to stay away from these kinds of PetriNets. Let me now talk about some of the other characteristics of PetriNets that are important. Now we discuss the case of starvation. In this particular PetriNet, with the marking that we have, this PetriNet can go into a starvation situation. Here what happens is that if we fire transition T2, it will take tokens out from both its enabling places and it will put a token into the target, and we will ultimately get this situation here. Now, once we are in this situation, in that particular case, what has happened here is now both transition T2 and transition T4, they have been starved. Note one thing here, that in this particular case, T1 and T3, they are still live. We can fire T1 and that will fire T3 and that will once again enable T1 and so on and so forth. But there is no way we can enable T2 or T4. So here we saw a situation which is slightly different from a deadlock situation. In this particular case, part of the network is dead, but the other part of the network is alive and it will keep working. That means, the part that is dead, those transitions in that part will never be fired, and hence, the processes that are represented by those transitions and places, they will be starved. So once again, we perform this kind of analysis, and this is kind of a liveness analysis. Whether part of the system is live or not, whether a certain state can be reached or not, and if we say, okay, if we ultimately reach this particular state, that means the system will be, let's say, deadlock, or this will be a starved situation. So we try to analyze this case, that okay, if we started with a given situation, could we eventually end up in this state, which will mean a deadlock or a starvation situation? And if we do that, if we find that situation, that means we need to work on our system, we need to remodel our system so that such a thing does not happen. It cannot happen in our system. In Petri nets, we have seen so many different scenarios and so many different cases. One of the most interesting problem in literature that deals with concurrent processes is the problem of readers and writers, which is known as reader-writer problem. And in this particular case, we say that we allow multiple readers in our system. Multiple readers can read, but only one writer can write, and when that writer is writing, no other writer or reader is allowed in the system. We can model such a thing with the help of Petri nets. How do we do that? Let me show you. So here is the model for synchronization control, the model of the reader-writer problem. In this particular case, we say that we will enable k simultaneous readers and only one writer. So what we have is, we have a very symmetric kind of a view, but we have given different weights to the arcs. So we have, in our initial marking, we have k tokens present in the two places that we have. The other two places, they do not have any token in them. So let us assume a reader comes. When a reader comes, it will take one token each from these two places, and it will deposit that token into the place that is labeled as reading. That means the writer cannot come in, because the writer requires k tokens in the middle place. We only have k minus 1 tokens. When the reader finishes reading, it deposits a token back into these two places from where it took the token. So what happens is that we can, since we have k tokens in these two places, we can have up to k readers, and as long as any reader is present in the system, we will not let any writer come into the system. So even if a writer is waiting, and if a reader is reading, that means if a new reader comes, then we will allow this new reader as long as the total number of readers who are actually reading is less than k. So this is a reader's preference problem. a model in which readers are given preference over writers. If some reader is already doing this reading, then we let other readers come in, even if some writers are waiting. When a writer comes, when a writer starts writing, that means it is only possible when we have k tokens present in the central place. So when a writer comes, it takes a token from the top place and it takes k tokens from the middle place and it starts writing. Once it finishes writing, it puts one token back into the top place and k tokens back into the middle place, and we are back to our initial state. So when a writer is writing, since all the tokens have been taken from the middle place, that means no new reader or writer can come into the system. So you saw in this particular example that we have handled the readers, writers, but in this particular case, writers do not have any preference over readers. And rather, if a reader is present, it will allow other readers to come in, while a waiting writer will have to wait till the time when there is no reader in the system. So it gives preference to the reader if the reader is already there. So it is a weak reader's preference model. If we wanted to model the system where writers are given preference over readers, it is not easy to do that with our normal petri nets. So in those kind of situation, there is an extension of petri nets known as zero test petri nets. Zero test petri nets, they are kind of this thing, they give us this situation, that is when some event is not present, or some place or some transition is not enabled, or there is no token in a given place, only then the transition that is related with that place is enabled. So it is the opposite of our regular enabling transition. What happens regularly? That is, we have transitions, they have input places, and we say if the places that provide input to the transition, if they have the required number of tokens present in them, then the transition is enabled. In the zero test, we say any particular place, the transition will be enabled only when all the transitions which we use normally, they have the required number of tokens in those places. Whereas this place for which we have applied the zero test, this transition will only be enabled when this place has 0 tokens in it. And this gives us a very powerful mechanism which is not otherwise possible in our regular petri nets. Let me show you an example of a zero test petri net. In this petri net, we have this transition A, B, C, and D. In transition D, we have an arc coming from this place, from top into the transition, with a small circle on that. This circle means that this transition D is enabled only when there is no token present in this place from where this arc is coming, with this associated circle with that. So this is a zero testing network, petri net. So here is a producer-consumer problem with priority. In this particular case, we are saying that consumer B can consume only if buffer A is empty. That means there is nothing in buffer A. That means the consumer A cannot consume because buffer A is empty. Only then we allow consumer B to consume. So here we saw an example where we are giving priority to one set of processes over others. Here we are saying, okay, you can do work only when I cannot do my work. So as long as I am enabled, as long as there is something for me to work on, I will do that, and I will give, for example, the processor to you only when I have not enough work for me to do. If I'm sitting idle, only then you may go ahead and do your work. The petri nets, they have other extensions and variations as well. One of the very important extension is what is called a timed petri net. A timed petri net is a petri net in which we associate certain times or upper bounds in terms of time with certain transitions. And this is important in many situations. For example, let us look at this very simple petri net that represents a communication protocol. In this petri net, what happens is, as you can see, that we send a message to the receiver, and the receiver has to send an acknowledgement back. Just imagine that the acknowledgement never arrives. If the acknowledgement doesn't come back from the receiver, for whatever reason, maybe the receiver never received the message, the sender cannot continue sending more messages. So what we have to do is, we have to have some mechanism in which we can time out the transactions, and we say, okay, we will wait for this much amount of time for the acknowledgement to come back, and if that does not happen, then we will resend this message again. If this acknowledgement comes back within this specified period of time, we are fine. Otherwise, we will resend this message again. This can only be done with the help of timed petri net, where we associate timings with our petri nets, with our transitions in the petri nets. So here we saw a very simple example of timed petri nets. These kind of things are not possible otherwise without these kind of extensions into petri nets. And note one thing here, and remember that in our concurrent systems, such things are very common. We need to have mechanisms to handle these situations where, when two processes, they exchange messages, for whatever reason the other side is not able to receive the message. Maybe it is dead, maybe it received the message and it sent the acknowledgement back, but for some reason the message was lost in the system, or maybe when you sent the message, the message was corrupted, and hence it needed to send you back this thing that, okay, there was something wrong with the message, you need to send again, and you never got the message back. All those different cases, when we have distributed concurrent systems, when we send messages, we need to have proper handshaking mechanism available, and that requires a timeout facility so that message can be regenerated, and you don't have to wait for acknowledgement forever, because there could be several reasons because of which the message never reached the other side, or it did not come back to you. The acknowledgement did not come back to you. Maybe there was some problem in the media, maybe some connection breakage, maybe any other problem. And if we do not have something like that to take care of this situation, then we will wait forever, and that will be kind of a deadlock situation, because you sent a message to the receiver never got it, you never got the acknowledgement back, and you are waiting for the acknowledgement, and receiver is waiting for the message, and it never happens. Petty nets, they have other extensions also. One of the extensions that I mentioned earlier was what is known as colored nets, in which the tokens are colored and they represent different types of resources. They do not actually add anything to the system, overall expressibility of the system, but yeah, I mean, they give you some additional information that can be used and is useful in, you can visually see things, and you can easily analyze things, and you can easily detect what is going to happen in that particular case. But the zero-test Petri net, it has been shown that this is equivalent to a Turing machine. So anything that you can do with a Turing machine can also be done with a zero-test Petri net, which is otherwise not possible. So this is a long discussion. Petri net, we just touched the surface. The purpose was just to introduce Petri nets to you, and I hope you have got some idea of what Petri nets are. There are other schemes, other mechanisms that we use in concurrent systems, but unfortunately, we do not have time to discuss all these different things. So I conclude my discussion on Petri nets here. Inshallah, in the next lecture, which will be our final lecture, I will try to conclude and sum up what we have discussed throughout this course. So till that time, Khuda Hafiz or Assalamu Alaikum.